Okay, so in this video, we're gonna look at the practice problems for test 2. Because last video I did cover 4.789, and then test 2 will cover 4.3 to 4.9. Okay, so and then yeah, so I'm gonna go through the 4.7 section 4.7 to 4.7 to 4.9. I'll try. Okay. Then because the last video I didn't go over many examples. Okay, so I just introduced the PDF and the CDF of the several the probability distribution. So from the exponential distribution, we'll see the practice problems as example. Okay, so give me a second. Yeah. So the first problem is this from 4.7. So web the crawlers need to estimate the frequency of changes to website to maintain a current index for web search. So then assume that the changes to a website follow a pausing process with a mean time between changes of 3.5, and they let a random variable x denote the time until the next change. Definitely these problems relate to pausing process, but they look at the random variable x. Random variable x doesn't mean the number of changes, but the time. So that's why this is problem about exponential distribution. I mean, you have to apply the exponential distribution. Okay, so back to the, yeah, you can open that, that window in your, in the really plus. Okay. Now back to the, yep. Give me a second. Back to the paper. All right. So, excuse me. So let's see. 4.7 and problem number 2. Okay. So random variable x in the problem says that the mean time in days until the next change. Okay. So definitely thus x is an exponential random variable because in a exponential distribution, the random variable x means the time or length until until the first event occurred. Okay, normally first success occurred. Okay, so here in the next one, the problems. Let's see this one. What problem mentioned? Mean time between changes of 3.5 days. So mean time means what? This is the expected value, mu, right? So E of x is 3.5, but exponential random variable, can you see that? Exponential random variable, the expected value, the formula is 1 over lambda. Okay, so mean time between change of 3.5 days, which means that 1 over lambda is 3.5. So lambda must be 1 over 3.5. And then exponential random variable, the PDF is what? Lambda times e to the negative lambda x. Okay. So this and the CDF going to be 1 minus e to the negative lambda x. Okay. So the first question is what is the probability that the next change occurs in less than 2 days? Okay. So it means that we got to find the probability that x is less than 2. Actually 2.0 days. Okay. So what is x? X is a time until the first change occurs. Okay. So then this is actually what? Nothing but f of 2, right? Actually f of 2.0. Because x is less than something, that's the CDF, right? Okay, cumulative distribution, right? So this is equal to then 1 minus e to the negative. We got lambda, right? Which is what? 1 over 3.5. So 1 over 3.5 and then times x is 2. Okay. So you just, yeah, and then it's not a big deal to, calculate this one to get the decimal exponential using calculator, right? So, okay, I'll leave it. But anyway, the answer is approximately 0.435. Okay. So now next one, question B. What is the probability that the time until the next change is greater than 7.0? So we got to find out this, right? X is greater than 7.0. Okay. By the way, back to the question A. So yeah, I just apply the CDF right there. Or you can say that this is equal to what? 0 to 2.0 and then f of x dx, isn't it? Okay, you can say that. So which means that what? 0.0 to 2.0 and then what is f of x? Lambda times e to the negative lambda x dx. Okay, you can just evaluate integral. But what? Definitely, what? Applying just the CDF is much easier than evaluating integral, right? So that's why I use this one. Excuse me. So now back to problem B. This is what? Probability x is greater than 7.0. It means that, but as you can see that what? Probability x is 7.0. Let me, this is equal to, what does that mean? X is greater than 7.0. It means that the next change, it will, x is greater than 7.0. It means that time until next change occur is greater than 7.0. It means that in a view of Poisson process, the event will not be occurred within 7 days. So this is nothing but probability that n equals, I'm sorry, it should be 0. Yeah, but yeah, n equals 0. But yeah, you can say that, but let me use other way. Okay, so 1 minus, let me do this. Sorry, this is the, we can do this. We can do this. This is equal to, actually, yeah. Let me do, sorry, let me do this. Probably that n equals 0. Because I'm going to do this one in a problem C, but okay. So this is equal to then what? What's this? N is, yeah, let me cover C first. Then you can understand, then I'll back to B, okay? So C, in here, we need this one. Probability that x is greater than x. This is equal to probability n equals 0. What is a capital letter N? That is the random variable in a Poisson distribution. So N denotes the number of changes in x days. So number of change in x days equals 0. It makes sense, right? Because probability x is greater than 0, x, it means that the next change will not be occurred within x times, x days. So there will be no changes occurred within x days in a view of Poisson process. And then the what? In a Poisson process, the PMF, because the Poisson process is a discrete random variable, right? So the PMF is going to be this: e to the negative lambda x times lambda x n over n factorial. So applying this one into here, can you see this? So we're going to get this: e to the negative lambda x 0 over 0 factorial. Okay, because 0 factorial 1, lambda x to the 0's power 1, so we got e to the negative lambda x. So probability x is greater than x is it what? E to the negative lambda x. So this is e to the negative lambda x. Okay. So now, oh yeah, so then was x 7, was lambda 1 over 3.5. Okay. So yeah. So this is equal to e to the negative 1 over 3.5 times, what is x? X is 7, right? Times x, 7. Okay. So this is approximately 0.135. Okay. Now C. Okay. Now C. Question is this. Oh, where's the question right here? Give me a second. Oh, yeah. So what is the probability that the next changes occur in less than 10 days, given that it has not yet occurred after 3 days? So therefore, this is a conditional probability, right? So next occur in less than 10 days, given that, whenever you see the given that, then that's going to be conditional probability. So we can say that, we can say that the problem is nothing but finding probability that x is less than 10, given that x is greater than 3, okay? So, but this is equal to probability that x is less than 7. Why? Because of lack of memory property. What's the lack of memory property? So think about this. Here's the 0 days from the 10 days, okay? So we want to find out the probability that the next change occurs between 3 to 10 days, okay? So when you find the probability that the next change occurred, the time until the next change occur is between 3 and 10 days, will not be affected by the probability in an exponential distribution 0 to 3, I mean past time passed, okay? So this is nothing but just 0 to 7. That's a lack of memory property, okay? So then, yeah, that's why this is equal to this. But we already got this one in problem B, right? Is problem B. This is equal to what? Approximately 0.135, right? Okay. So now, but the problems D, what? See right there. Give me a second. C. Oh, it's problem D, right? I just confused with the problem C and D. I'm sorry. So back to here. Okay. So back to here. I'm sorry. I didn't get the answer for C. Sorry, it makes you confused. So back to here. C is what is the time of next change that is exceeded with a probability 90%. So we want to find out the time where that probability equals 0.9. Okay. But this is equal to what? E to the negative lambda x. So we have to solve what? E to the negative lambda x is equal to 0.9. Okay. So and what is lambda? 1 over 3.5. So this is equivalent to what? E to the negative x over 3.5 is equal to 0.9. Okay. So the other pages. So then here we solve it. We take a natural log, right? So negative x over 3.5 is equal to natural log 0.9. Okay. Then what is x? X is equal to negative 3.5 times natural log 0.9, right? Okay. So this is approximately 0.369 days. Okay, so this is the answer. So that's then D, back to D, sorry. All right, the so question was, what is the probability that the next change occur in less than 10 days, given that it has not yet occurred after 3 days? So I told you by the lack of memory property, this condition probability is equal to this. Okay, and then we got this one in problem B, so the answer is 0.135. All right, that's the question problem 4.7.2. Okay, any questions, let me know. So then let me see. Next one. Next problem is, give me a second. This one. Oh yeah. So for next one. Oh, okay. So question is this: request for service in a Queening model follow a Poisson distribution with a mean of 5 per unit time. So average number of requests is 5 per unit time. Okay, so see, and then what is the time? I mean, when you just look at the problem, this is a problem about Poisson process, right? But look at the question A, B, and C. What is the probability that the time until the first request is less than 4 time unit? So the equation A is asking you to find out probably that the time until the first request. So the problems give us the Poisson process, Poisson distribution, but the question is about exponential distribution. So we have to the construct the what exponential distribution. I mean, what's the meaning of the exponential distribution with random variable and then PDF and then the mu and sigma square from the what Poisson distribution given in problem. Okay, so the now here 4. This is question problem 3, right? 4.7.3. So let n denote the number of requests with a mean of 5 per unit time. So n denote the number of requests. Okay, I just use a capital letter N. Okay, so this is a Poisson random variable. Okay, and then definitely, right? And then the mean of time 5. This is lambda, right? Mean of 5 requests. So they got the 5 requests per unit time. Okay, so okay, you can say this 5 is the mean rate of requests. Okay, so now the next one. So we're going to construct the exponential distribution associated with the Poisson random variable. Okay, so let x denote the time unit, the next request, actually next the first request. Okay, so now then think about this. Here is the kind of timeline. Okay, so the unit is certain time unit. Okay, first request, second request, and third request. Just keep going, right? Right. So then the what? The probability that x and then here then probability what? Right there. I mean until right there. So to find out when you find the probability that, for example, x is less than d3. Okay, so what that means, for example, there that means the probability that what the time until the what the next request is less than 3 time unit. Okay, so right here and right here. So this second request, after the second request, I want to figure out the probability that next request, which is third request, right? I want to figure out the probability that third request will occur will be less than 3 time unit. Okay, so maybe, so here this is 1, 2, maybe 3. Okay, it's a 3 time unit. Yeah, totally we don't know how many time units between the second and third request. Okay, also the I want to just make sure that what for each first request can be considered as a first request because of lack of memory property. Okay, once the second request occurred, then we can consider third request as a first request. Okay, because of the lack of memory property. Now, okay, back to question A. So what is the probability that the time until the first request is less than 4 time unit? So yeah, that's what we figured out this one. We need to figure out that one, right? This is nothing but what? CDF. What's this CDF in exponential distribution? This one, 1 minus e to the negative lambda x. Okay, so now 1 minus e to negative lambda x. So what is lambda? Lambda is 5, right? So 5, and then x is 4. So the this is equal to 1 minus e to the negative 5 times 4. Okay, so think about this. E to negative 5 times 4. This is almost 0. Okay, so yeah, this is actually 1. Okay. All right, so now next one, B. What is the probability that the time between the second and third request is greater than 7.5? I told you between second and third, then we can consider the request as the first request. So we find that probability that x is greater than 7.5. Then this is equal to what? We use this one. You see that probability that x is greater than x is what? Equal to e to negative lambda x. Okay. So we got e to negative lambda times 7.5. Since lambda is 5, so we got 7.5. So this is also almost 0, right? It's almost 0. All right. Next one, C. Oh, who is C? Okay. Determine the mean rate of request such that the probability is 0.9. I'll show you. Okay, I'll show you the question. Okay, so determine the mean rate of request such that the probability is 0.9 that there are no requests in 0.5 time units. Okay, so so what's the mean rate of request? Lambda, right? Lambda, right? Okay, so probability is given. Okay, and then 0.5, that's the time, okay, until the next change occurred, right? So, oh, see, stop here. Yeah, so the what? Expressing the quotients in mathematics, we can say the probability that x is a 0.5, that is equal to 0.9, okay? But we know that probability x, right there, see, probability that x is greater than x is equal to what? E to negative lambda x, right? So probability that x is greater than 5 is equal to e to the negative lambda times x, which is 0.5, is equal to 0.9. Yeah, so we'll be for lambda, okay? So then what? Negative 0.5 lambda is equal to natural log 0.9, 0.9, okay? So lambda is equal to what? Negative 2 times, is it? Natural log 0.9, right? Okay, this is approximately 0.211. Okay, so next question. Next question is really interesting. So share screen. All right. So if the service times are independent and exponentially distributed with a mean of 0.4 time units, what can you conclude about the long-term response of this system to request? All right. So then we need to figure out the how many services can be done in one time unit. That's called the service rate. Okay, then we compare the service rate with the how many requests of how many requests they can receive in one time unit. Okay, so that's called the arrival rate of request. So we need to compare them. So right there, so in one time unit here, okay, first one, we know the mean rate of request, which is 5, right? What does that 5? It means that every 0.2 time unit, the request is arrived, right? 1, 1, 1, 1, 1. I mean, in view of, in the sense of average, okay? So then arrival rate of request, this is a 5, right? This is given. This is a lambda, right? Then the problem says that in D, the service times are independent exponential distributed with a mean of 0.4 time units. It means that every 0.4 seconds, they gonna complete the service the request, right? Then in one time unit, they can complete 2.5. They can complete the 2.5 services. So service rate gonna be 2.5. Then see that here, just use the common sense. The service rate 2.5 and the arrival rate is request 5. Then what happened in long term? Then the service request gonna be increased, right? Okay. So the question is, what's the answer? So in the long term, the queen of service requests is expected to continue to increase because what? The service rate is less than the arrival rate of request. Okay, so that's the answer. So now then, and then that's the 4.7 point problem 3. Okay, so any questions? Let me know. So now we're gonna move to 4.8. Okay, 4.8. 4.8 is about Erlang distribution and then gamma distribution. Okay, so let me see. Okay. Yep. Okay. Excuse me. So 4.8.2. Yeah, this is. I don't think that this is this problem is difficult. So let's see. We model the gene mutation of a virus as a Poisson process. Okay, suppose a virus mutates once every 3 months on average. Okay. By the way, so and then the question A: what is the mean time until the fourth mutation? All right. So you may just confuse with the exponential distribution and the Erlang distribution. Do I have to apply the Erlang distribution, or do I have to apply the exponential distribution? So what's this difference between them? So first one, I told you, exponential distribution is what? The random variable of x denote the time or length that the first event occurred, okay? Until the first time occurred. But Erlang distribution is the random variable of x denote the what? The time or length until r event. So here r is the natural number, okay? R event occur in a Poisson process. So both distributions based on built-in based on the Poisson process, but Erlang distribution is more general than exponential distribution. Keep in mind this. Then how can we know that we have to apply Erlang distribution in a problem? You see that what is the mean time until fourth? Okay, that doesn't say that next, or that doesn't say that first, this is fourth. It means that R equals 4. So we have to apply Erlang distribution, okay? So now, yeah, so back to the my note right there. Okay, so Erlang distribution, I told you random variable x denote the length or time until R events occur in a Poisson process. So probability x is greater than x, what does that mean? Probability that the length or time until R events occur is equal to what? It means that in a view of Poisson process, the number of events, see that, occur in a limited the time or the finite length must be r minus 1. Okay, you see. Why? Because I told you, you think about this here, the timeline here is 0, and then it says x. Okay, so probability x is greater than x means that it did happen the r minus 1 event within 0 to x. Okay, happen. This is first event. Okay, first event and second event, third event through the r minus 1th event. Okay, event, and then probability x is greater than x. That means the rth event occurred after time x. Maybe here, maybe right here. This is the rth event. Okay, Then in a VO parsing process, probability that x is greater than x means that probability that the n, which is a random variable in a parsing process, denoted by what? Denote that what? The number of events, okay? So occur in x time, okay? This is must be less than or equals r minus 1, right? From here to here, okay? But we know the what? A PMF or parsing process, actually CMF or parsing process, which is a sigma, and then this is the PMF, right? Okay, n is less than or equals r minus 1 means that what? This is equal to what? Sigma probability that n is equal to what? K. Okay, so k is equal to 0 through r minus 1. Okay, what is this? This is equal to this is equal to what? The PMF in parsing process. Okay, can you imagine this? So we got this. Anyway, so then and then I skip. Yeah, so from here we can get the derive the PDF of the Erlang distribution, which is this. I know it's a little bit complicated. Okay, but please be familiar with this. Okay, so lambda to the r, x to the r minus 1, e to the negative lambda x over r minus 1 factorial. If r equals 1, that PDF gonna be exactly same as PDF in an exponential distribution. Okay, and then mu is r over lambda. By the way, in an exponential distribution, mu was what? 1 over lambda. Okay, and then the variance is gonna be r over lambda square. In exponential distribution, lambda square, the variance was 1 over lambda square. Okay, so now the question A, is question A right there? Not here. Okay, so question A. So what? Lambda. Give me a second. A what? What is the mean time until the fourth mutation? So okay, so mu was what? Is it r over lambda, right? Okay. The problem says that r is 4, lambda is what? Once every 3 months, right? So lambda is 3, right? Okay, let's see. Let me show the oh, give me a second. Oh, okay. Lambda, what is lambda? Suppose the virus once every, so you see that once every 3 months on average. Okay. So which means that this is a mu, right? This is the mean of the exponential distribution. So suppose a virus mutate once every 3 months. So that means the event, an event occurred every 3 months, which means that the mu, which is the mean of the exponential distribution, is 3. But we know that in an exponential distribution, the mu is what? Is 1 over lambda. So this is 3. So lambda is what? 1 over 3, right? So we're gonna plug in this one right there. Okay, so this is 4 over 1 over 3, which is 12. Yeah, this is the answer. Okay. Now B, what is the probability that more than 5 mutations occur in a year? What is the probability that more than 5 mutations occur? We find the probability that what? The x is greater than. Oh no, not this one. X is greater than in a year. Year is what? 365 days. Why did I convert the unit? Time unit year to day, because the problem says that what? The lambda, the time unit in the lambda is Give me a second. Is that, you see, let me see problem. Month, right? Not this one. I'm sorry. I confused with other problem. 12, right? Okay. Because a year means the 12 month. That since the unit of lambda is a month, so I had to convert the year to month, which is 12. Okay. So we see what is the probable that more than 5 occur. Okay. Give me a second. Okay. Now let's see. Now, let's see. All right, then this is equal to, yeah, this is equal to sigma. We see that here, right there. Probably the x is greater than x. So let me see, will occur 5 year. Yeah, give me a second. I'm sorry, I confused with this. That more than 5 mutations. Oh, I see. In a year. Okay. Then we have to define new random variable. Now let's see. Sorry. So let's see. Let's say the problem B was probably that more than 5 mutation. Here. Okay. So then now we say that let y, x, z, whatever. Let's see, x, y, z. Okay, let's say y. Okay, y denote the, because see actually, yeah. Okay, let me do this. Okay, y denote the time in month until the 6th mutation. Okay, because we need to kind of define new random variable in the Erlang distribution. Okay, so in the problems, yeah, we can solve this one. I think we can solve this one using the Poisson distribution, but yeah, I'll show you later. Okay, but first of all, let me try to solve this one using the applying the Erlang distribution. Then to apply the Erlang distribution, we need to define Erlang random variable, right? First one. So let why denote the time in month. Okay, in month until the 6 mutations. Oh, mutation. All right. So then, y gonna be Erlang distribution, right? It's not until the 1st, so until the 6th. So that's what y is Erlang distribution, right? So now then, f of y, f of y is gonna be the lambda to the rth power. F of y gonna be lambda to the rth power and the y to the r minus 1 and the e to the negative lambda y over r minus 1 factorial, right? Okay. So now what is r? Here r is must be what? D6. Okay. And then lambda gonna be, we just got, we figured out lambda in a previous question, right? It's right there. It's a lambda 1/3. Okay. So now then probably back to question B, what is the probability that more than 5 mutations? That means probability that y is in our year, that means y is less than or equals 12. You can say that. Okay. So since the problem said that more than 5 mutations, then the at least 6 mutations should be occurred in a year. So that's a y is less than or equals 12. This is equal to what? 0 to 12. Okay. And then f of y and dy, isn't it? Okay. I know this is not easy because you know, because what? This is equal to 0 through the 12, and then f of y dy is what? 0 to 12, and then fy is lambda to the lambda is 1/3, 1/3 to the r's power, which is the 6, and then y to the 6 minus 1, and e to the negative 1/3 times y over, and then 6 minus 1 factorial, okay, dy. But you can see that here, I mean, this is equal to, and then 1/3 to the 6 power over and 5 factorial. This is constant, so I just take out the integral, so 0 to the 12, and then y to the 5th power e to the negative y over 3 dy. So to evaluate the integral, you see that here, this is a polynomial, this is exponential function. So you gotta apply the integral by part, not just once, but I think at least the fourth times. Yeah, so, but I'm not gonna do that, okay? But yeah, you may just figure out the, you may just evaluate this one using calculator, okay? And do it, then you're gonna get the answer approximately 0.21, okay? So that's the problem 4.8.2. Next one, let's see. 2, 4.8.3. Okay, so let's see. Okay. All right, so show that the gamma density function integrate to 1. Okay, so what's the gamma function? Gamma function is the the generalization of Erlang distribution. In Erlang distribution, the number of event R was the natural number. But in the gamma distribution, the event R can be any real number. I mean, any non-negative real number. Okay. So this is more general, and the gamma distribution is more general than Erlang distribution. Okay. So Erlang distribution, gamma distribution, the pretty much the same. Okay. But the meaning of the random variable different. I told you the gamma distribution R can be non-negative, any non-negative real number, but Erlang distribution R should be natural number. Okay, all right. So now then, and then let's see right there. Okay, so in the gamma distribution, the what? The PDF gonna be lambda to the r's power x to the r minus 1 times e to the negative lambda x, which is exactly the same as numerator in a PDF in an Erlang distribution. The denominator is not r minus 1 factorial, this is a gamma r. Why? Because of the gamma distribution, gamma r is equal to what? R minus 1 factorial. Okay, and then if R is the a real number, is a natural the natural number, gamma R is equal to R minus 1 factorial. Okay, and then yeah, you see that you can see a set of property of the gamma function. This is a gamma function. Okay, gamma function in my lecture note. Okay, so R is a natural number. Then this PDF can be exactly equal to, I mean, will be equal to the PDF in Erlang distribution. Okay, so mu and sigma square is exactly the same as the mu and sigma square in Erlang distribution. Okay, so now problem is this: 0 to infinity. Yeah, so I mean, I think I'll show the let's see the problem. Okay, so you see, what's the expression one? So f is what? Gamma density function, which means the PDF, okay? PDF of gamma function. We know PDF gamma function, right? Lambda to the r's power times x to the r minus 1 times e to the negative lambda x over gamma r. Okay, so the next one is let what? So next one, let y equals lambda x. They just change a variable. Okay. Then so 0 through the infinity. I mean, let's say y is equal to lambda x. Then what? The lambda to the r's power x to the r minus 1 e to the negative lambda x over gamma r. This is equal to, let me try to express the x in terms of y. That's what they want, right? Okay. All right, so then now then, lambda, I mean, what? The lambda r times x to the r minus 1. So we have to express this one in terms of y. Then I take out the lambda from lambda to the r's power, then lambda to the r minus, then we get this, lambda times x to the r minus 1, right? And then e to the, you see that? Y is equal to lambda x, which means that x is equal to y over lambda, right? So we plug in y over lambda into x. Then we got the e to the negative y, right? And then lambda x, this one is equal to y. This is y over gamma r. Right? So what that means, lambda to the r's power times x to the r minus 1 times e to the negative lambda x over gamma r is equal to lambda times lambda x to the r minus 1 and the e to the negative y over gamma r. And then this is equal to lambda times y to the r minus 1 e to the negative y over gamma r. Okay, so now then 0 to infinity, and then lambda to the r's power x to the r minus 1 e to the negative lambda x over gamma r dx is equal to, we say, let kind of use substitution. Okay, let y is equal to lambda times x, then dy is equal to lambda times dx, right? So dx is can be changed to what? Can be expressed as 1 over lambda times dy. 1 over lambda times dy. Okay, and then, well, in that integral, I know this is not that integral, actually improper integral, but let me figure out the lower limit, upper limit after use substitution. So when x equals 0, y is going to be 0. As x approaches infinity, y approaches infinity. So lower limit, upper limit is just the same as 0 and infinity, okay? And then the integral is going to be lambda times y to the r minus 1 e to the negative y over gamma r. Okay, so what's the expression 2? This. This is expression 2. Okay, so, yep, right there. Okay, so yeah, this, so I just make use substitution, substitution u equals the y equals in lambda x. Applying the use substitution technique, yeah, we got that expression. Okay, so that's the problem 4.8.3. Okay, and then okay, let me take a break around 10 minutes. Okay, and then I'm gonna to give the second video lecture. Okay, so let me stop here. Okay, and then yeah, so let's see. Yeah, I'm gonna make a second video covering 4.9 problems, maybe 10 minutes or 20 minutes later. Okay, so you can join this meeting, or just you have other schedule, then definitely I'm gonna you can watch it through the YouTube. Okay, so I'll post this video in the next video in the YouTube, and then I'm gonna post the link in the Blackboard. Okay, so and any questions, just send the email, or while giving lecture, just ask to me. Okay, all right, so let me stop here. Okay.